play an important part in the study of radar indicators, and by now you should be able to recognize a pip when you see one. Some are tall, some are short, some are friendly, and some indicate danger ahead. That's the way it is in radar, too. Pips indicate all kinds of things. An enemy task force maneuvering through fog or darkness, our own reconnaissance planes, the splash from a coast artillery shell, the answer to an IFF challenge, or perhaps this is the signal returned from an enemy rocket ship or guided missile. The electronic eye of radar detects and locates these targets. But for this information to be of any value to you, we need different types of oscilloscopes to present this data visually, accurately, and effectively. Some scopes measure range only. Others measure either azimuth or elevation. Some present data on both range and azimuth at the same time. And still others measure both azimuth and elevation. Now you'll see how these scope presentations are formed and how the scopes display the data they obtain. In the first film of this series, we reduced all radar sets into this simplified block diagram. You saw how the timer generates a voltage pulse and sends it along to the transmitter. At the same time, it sends part of each pulse to the indicator, where it starts forming a baseline. Back at the transmitter, the pulse is converted into high-frequency energy, sent to the transmitting antenna and launched into space. However, a spillover of this energy escapes into the receiving antenna and goes down to the indicator, where it appears on the baseline as the main bang. The sweep of the baseline is synchronized with the outgoing pulse, so it can measure the time it takes a pulse to leave the transmitter, reach a target, and its echo return. When the outgoing pulse strikes a target and part of the energy is reflected back to the radar set as an echo, the receiving antenna's job is to pick up the returning echo and shoot it along to the sensitive receiver. Here, the weak echo is amplified and sent as a voltage pulse to the indicator, so it can appear as a target pip. Basically, that's how all radars work. And in the first two pictures of this series, you saw in detail how the timer, transmitter, and receiver did their jobs. In this film, we'll see how the indicator functions. Let's take a look behind the panel and see how this typical A presentation is formed. This scope picture, as well as all others, are created by a special type of vacuum tube called a cathode ray tube. There are two basic types of cathode ray tubes: the electrostatic and the electromagnetic. These tubes produce all the scope pictures in radar. Let's see how they operate. First, to review what we know of the electrostatic tube. At the rear end of the tube is an electron gun, composed of a heater, cathode, grid, and focusing anodes. The cathode, when heated, gives off electrons, which are formed into a stream by the grid. The anodes accelerate the electrons and focus them into a beam. The beam bombards the fluorescent coating on the face of the tube and causes it to glow with a bright spot of light. These plates deflect the beam horizontally. When positive and negative voltage is applied alternately to the plates in the form of a sine wave, the beam is swung back and forth like this. But when sawtooth voltage is applied, it causes the beam to sweep across and snap back quickly. At normal speed, we get this picture, or an apparent baseline. The pips are formed by the action of the vertical deflecting plates, which bend the beam up and down each time a signal pulse is received. Thus you can see that the electron beam is affected by both the horizontal and vertical deflecting plates. This is the usual type of A-scope. But these two sets of plates, by working together, can form any number of different scope pictures. For example, by changing the polarity of the voltage on the vertical plates, you end up with an A-scope on which the pips appear as negative deflections, like this SCR 582. These scopes, on which the target appears as a single pip, are okay for early warning and range data, but they were not designed to give elevation and azimuth data. This is why. A pulse traveling through space follows a path closely resembling that of a searchlight beam, and the greatest intensity of the beam lies in a direct line through the center. The strength of the beam diminishes gradually to either side of center until it reaches a point of minimum strength at the edges. The pattern is called a lobe, which is nothing more than an imaginary plot drawn to indicate the intensity variations of the radar beam. Let's say we have a target in the center of the beam, where the intensity is greatest. The target will reflect a strong echo, and you'll get a good-sized pip on the scope. But if the target moves ahead of the beam to a point where the intensity is weaker, the echo will also be weaker, resulting in a pip that's barely visible. As you traverse the antenna to catch up with the target, the plane is in a stronger part of the beam, and you get a stronger pip. It's the same on the other side of the beam. Minimum intensity, small pip. Maximum intensity, full pip, always letting you know when your beam is pointed directly at the target. But here's why a single pip can't provide accurate azimuth or elevation data. When the target signal on your scope fades, did the plane move ahead of the beam, behind it, above it, below it, or is the signal just fading due to a faulty set? You have no way of knowing. And if you assume the plane's getting away from you and begin searching for it, there's a 50-50 chance you'll traverse in the wrong direction and lose the target completely. To remedy the weakness of the single lobing system, we switch this single lobe back and forth so fast that you have virtually two identical lobes. When you have a target, these lobes are represented on the scope by two separate pips, one for the right lobe and one for the left. When the target is centered between the two lobes, the pips balance. That is, they're the same height. But if the target gets off-center, naturally it's going to be in a stronger part of one lobe and a weaker part of the other. Here, for instance, the target's moved to the left, so the left pip gets bigger, the right one smaller. If the target moves to the right pip gets larger. To center the target, all you have to do is traverse the antenna toward the larger pip until the two pips are again balanced. Then you know the target is centered in your beam and you're exactly on target. Keep the pips balanced and you'll stay on target.